is we're going to be graphing piecewise functions. And so piecewise functions are a combination of those parent graphs. Seeing multiple graphs on one coordinate system. When is it? I would guess during fourth period. Yeah, I'm not sure. Okay, for starters here, just because we haven't graphed a few of these, I want you also to graph numbers 1 and 3, 5 and 6. So we've graphed everything but lines so far, so just a couple line graphs there. All right, so hopefully we know how to do this. Y-intercept 1, slope of 2, or 2x plus 1. Y-intercept 2, slope of 2/3. What does y equals 3 look like? Show me. Yes. So these are all the points where y equals 3. This is the y-axis, right? There's y equals 3. So it's the point 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. These are all the points where x equals -1. Vertical line. X equals -1 is technically not a function. Not only does it fail the vertical line test, it is the vertical line test. It's even worse. But we can still graph them. So remember which one's which. We'll come back to domain and range, but here's what piecewise graphs look like. It's just like we have part of a line right here and then another part of a line that takes over. We have a parabola and a line put together, a parabola and a line put together. What's important to notice about these is they will not fail the vertical line test because they are piecewise functions. So whenever you graph one of these, just give it a quick look over once you're done. Make sure it's not failing the vertical line test. So like in number 7, we have an open circle above a closed circle. So an open circle means there's no point there. And so wherever the functions overlap, there needs to be one open circle and one closed circle, at the very least. In number 8, we actually have 2 open circles, which means we have no points there. So while it looks like the functions are overlapping, they're actually not meeting at all. So we will always pass the vertical line test. This one here's just got a big old gap in between. So they will always pass the vertical line test. Okay, so we'll do some of these here. Start with the easy one. So this is what piecewise functions look like. I'm sure you guys remember this from last year as well. It tells us what we're graphing and then where we're graphing it. So this would be the what. This would be the where. So that means we're graphing y equals -4 for all x's less than 3. So that means I put an open circle at x equals 3, y equals -4. And I've got my horizontal line that I'm graphing for all those values where x is less than 3. Then where x is greater than or equal to 3, I'm going to graph y equals 2. So that's a horizontal line. And since it's greater than or equal to 3, I put a closed circle. And so there's our piecewise function. Let's do number 14 together. So for some of these, now this one's more complicated, right? Because it's not just horizontal lines. We have to graph like lines with different slopes. What I like to do, just to keep myself sane here, is I like to draw a dotted line at -1, just to kind of divide this graph into 2 regions here. Because that's where the graph changes, is there at -1. So I just like to remind myself visually where that is. And sometimes what I like to do is even just write down here, like 3x plus 2 and x minus 2. Because sometimes I just have problems like reading the greater than or less than sign correctly. I don't know if you guys resonate with that, but sometimes I just get them mixed up, which one's which. So I just like to write them, put them on the graph where I can see them. And sometimes just like reading that equation to actually putting it on the graph, my brain needs help. So I like to write it down there. So when I'm graphing the line 3x plus 2, this one's easier to do because I can put the y-intercept right there and then just do my slope of 3. When I go down 3, back 1 over here, I'm going to put an open circle there because that's where my graph needs to stop. It needs to stop at x equals -1. And I'm just looking up there to see that that's strictly greater than. This x minus 2 is slightly harder to graph because the part of the graph that it's supposed to be on does not include the y-axis. So I can't really put the y-intercept on the graph and then graph from there. What I like to do, especially with lines, is I like to just go ahead and put the y-intercept there anyway, and then I'm just going to erase it later. And I just like to graph like my slope of 1 like it would go that way. I don't really want to go that way anymore because the graph's not even over there. But I'm graphing it this way. And then since like this is actually where the graph is supposed to start, that's where I'll put my big old closed circle. And then I'll just erase this right here. Or there's another way that we can graph that. Turn to your neighbor. How could I get the coordinates of that point right there? Talk about it. Without using the y-intercept. Okay, so how could I get the coordinates at that point without using the y-intercept? How do I normally get y values from functions? Anna, what do you say?
Oh, plug it in.
Yes. Plug what in for x? -1, yeah. We just plug -1 in for x. Which function? Red one or blue one?
Red one.
The red one, yeah. That's the one that's going to be over there. I just plug in -1 for x, and I get -3. So this is the point, -1, -3. Then from that point, I can just graph a slope of 1, but going to the left where the graph is supposed to be. I usually like to do both to double check and make sure that I've graphed it right. Although typically what I prefer to do is just graph and erase. That's why I showed you guys that first. Once I'm done graphing the piecewise function, I do like to erase the dotted line because otherwise you might think it's an asymptote. It's not an asymptote. It was just helping me divide the graph into two regions. Okay, so in number 15, we've got slightly more complicated functions here. Notice our domain is also a little more complicated. It's a little more restricted here. So we've got one region here that goes from -4 to 0. And I'm going to graph x plus 2 squared in there. And then my other one goes from 0 to 6. And I'm going to graph 1/2 x plus 1 in there. If you guys like color coding things, it can be really helpful as well, just a way to help divide up the graph and make it easier to check your answer, keep track of which one you're doing. But so for the first function there, which I'll call the red function, that's just our parabola shifted left 2. So I go left 2, and then I just graph my parabola as normal. And I see I need to use a closed circle here for 0 because of that. And I need to use an open circle right there for -4. Then for the other one, I'm doing 1/2 x plus 1, so my y-intercept is 1. It's nice to have the y-axis, so I'll just put an open circle there and graph a slope of 1/2 until I get to 6. That will be a closed circle. There we go. We actually use piecewise functions all the time in calculus and then also in real world problems to model situations. Because it's very rare that a situation could always be modeled by the same equation the whole time. Usually what happens is like, a certain situation behaves like this for this amount of time, and then suddenly it starts behaving like this. And so like an example that we use in calculus is like you can model the number of people coming into a theme park for the first hour with like one of these graphs. But then after the first hour, because people are coming and going at the same time, the rate of growth looks a little bit more like that. Because still more people are coming in than are leaving, but some people are leaving, so the number of people inside is not growing as fast. And then after a certain point in the day, it starts to decline, and then everybody leaves, or something like that. So that's the kind of thing we do in calculus all the time. But also like any sort of like Like economists would use this to like try and predict what the economy is going to do, or I don't know, other stuff. Anytime you're trying to model a situation or make predictions, you usually need more than one equation, and so this is why we have piecewise functions to do that. So yeah, I want you guys to do numbers 16 and 17. With 17, don't be intimidated by the fact that there's 3 regions. It works the same way as 2, but instead of 2, you have 3. Give those a try, work together, then we'll check them. All right, guys, so let's check these. So with this one here, I'm not done yet. What do I need to do to finish number 16? Yeah. So I just put that y-intercept there to help me out. This is more what it should look like here. I like to erase the dotted line. So I just had to go up to 5 and then count down by -1s to make sure I ended up in the right place. Or I could just plug in the point 3 for x right there. -3 plus 5 is 2. I should be at this point 3, 2. Same thing in number 17, like I haven't yet erased my line for -x plus 2, so I'll just erase that right now. What's interesting in this one is that the blue graph, which is y equals -1, it ends with 2 open circles, but those open circles are actually filled up by the closed circles from both red graphs. So this function is, we would say this function is continuous. We'll talk more about continuity, but there's no breaks in it at all because it kind of fills in those missing pieces there. So -x plus 2 squared is just our parabola shifted left 2 and going downward. And then -x plus 2, I had to do the same thing where I counted down from positive 2. Questions on either of those? Okay. I'll leave the other ones probably for our warm-up. Well, the other one. There's just one more. Probably for our warm-up when we come back from spring break. See you soon. Okay. Here's the other thing that we're going to be doing is the reverse. Writing piecewise equations represented by graphs. So on the, this is where the like function goes, and this is where the domain goes. And, we can see where this is happening here. So first of all, this one has an arrow pointing to the left, which means it's going on forever. And that function starts there at x equals -3. So this would be x for all x less than -3. Would it be less than or equal to? Less than, yeah. How do you know?
Open circle.
Yeah, exactly. Okay, and what function are we graphing for that part? Y equals 6, yep. So we just write 6 because we already have the y equals, basically, the f of x equals. So we just write 6 for x less than -3. Okay. What's our next section go from? From where to where? From -3 to 0. Yeah. So this kind of looks like an absolute value graph, but we can see the slopes are different, so it's not absolute value. It's 2 separate lines, so we need to do 2 separate equations here. So we're going to write -x less than 0. Less than 0 or less than or equal to? So actually we have an option. It actually doesn't matter. What matters is the next section here when it's x greater than 0. Between these two, one of them needs to be equal and one of them needs to be not equal. So we'll say exactly one needs an equal sign. And it doesn't matter as long as exactly one. Having 2 would be wrong. It would fail the vertical line test. You'd have 2 points overlapping. Having neither one with an equal sign would be wrong because then we would have an open circle right there, which we don't. So it truly does not matter. Up to you. Whatever your heart's desire. So I can see the equation of that line right there is negative x plus 3. I'm looking at the slope there. I'm looking at the y-intercept. And this one looks like it's 1/4 x plus 3. Questions on that? For the next one here, when we're coming up with these equations of these lines right here, so let's say we're trying to do the one here for x less than, let's say less than or equal to -3, this one. You have the option. That one is really hard to tell what the slope is, huh? Let's say that slope is, we'll make it really crystal clear on the test what the slope is. We'll say that's a slope of 2/3. We could count up to over 3 and see that the y-intercept would be 10. So this would be 2/3 x plus 10. What we can also do, especially if the y-intercept is not a whole number, like it doesn't line up good, or if it's like look at this one, we're gonna have to count down really, really far. We might not get there. It might be too steep. What we can do is use our handy dandy point slope form. And so what that would look like is for this one here, let's use that point -3, 8. So it would look like y minus 8 equals 2/3 x plus 3. We can't quite put that into our equation here because it needs to be solved for y. So how would I solve this for y right there? One step away. Add 8 to both sides, right? So we could just write 2/3 x plus 3 plus 8. Now also think about what that means. That's a line that's shifted left 3, up 8. Right? Exactly where that point is. So just think of it as like transformation form. So sometimes that'll be a lot easier to do. But we could do that for the next one. Like that's a slope of -4. I could use this same point. X plus 3 plus 8. And we'll use that for -3 is less than x, less than or equal to -2. I can distribute if I want, but I don't need to. I can just leave it like that. I could also use this point. X plus 2 plus 4. It's the same line, same equation. You guys do the other two parts of this for the horizontal line there and that one. All right, yes. What would we get for that one right there? What would we get for that one? What is it? 4. Nice. Let's see. So this should be -2 less than x, and then less than or equal to 4. Okay. So we need to do less than there because we did less than or equal to right there. But you could also switch them. Up to you. What'd you guys get for the last part? 6x minus 20? Okay. Did you count all the way down, or you did? Yeah. Yeah, we can count all the way down. Or did anyone do 6 something else? Yeah, Jack, what did you do?
I did 6x minus 4 plus 10.
Okay, so if it's -4, it wouldn't be plus 10.
Oh, it would be plus 4.
Yeah. If we wanted plus 10, we would have to do x minus 5 plus 10. Yeah. We can check the math there. They all do work out to equal 6x minus 20. So that's just a way to check that they're all the same. Okay, and so this would be from 4, then what? Less than x less than 5. Yep, nice. Okay. I'll just divide those up on here so that's a little more clear. Okay. Last thing we'll do for the notes today is want to review some just like function notation. When we say f of -4, what equals -4, x or y? X equals -4. Okay. So we have to go to where x equals -4 on this graph. Boom, 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 boom. That's right there. And so we would say f of -4 equals 0. Yes. Because that means x equals -4, but the f of means tell us the y coordinate. F of -1. It's not there. Okay. Does anyone know the official way that we say this? Does not exist is not quite right. We will use that phrase for limits, but not for this. What we say is undefined. So undefined means like the point is not in the function. It's the same thing that happens at a vertical asymptote. There's actually no point there. But it's when the point is missing. Thank you. Okay, f of 3 equals f of 3 equals 4. Yeah, that point right there. Okay. Then when we say f of x equals 0, what is equaling 0 then? X or y? See? Yeah, this is y equals 0. So there could be more than one answer for this. In this case, there's not, but we look and see where does y equal 0. It's right there at x equals -4. But there can be more than one answer. If f of x equals -4, we look down here where y equals -4, we see, oh, it's right there at x equals -2. That's just a reminder. Go ahead and do the domain and range of this graph. All right, so here's what we should get. Let me just remove that y right there because it looks like. So our domain has a gap in it right here. So we have a closed circle here at -2, or a bracket at -2, and then a parentheses at -1. Our range does not have any gap in it. When we get to y equals 0, there is a point there and an open circle on the other part. And then as soon as we go above 0, there's also a point there. So I used this analogy earlier in the year, but I'll remind you guys of it. Domain is, you imagine it raining. Where are there holes in your roof? Those are the numbers that you exclude. So it's like everything to the left of -4, in between -2 and -1, everything to the right of 3. For a range, imagine you're home on the range and there's a powerful windstorm coming. Where do you have shelter? You could actually stand right there and be safe from all the wind. This little gap right there would get stopped by that function. So that's how I like to do it visually. Okay. That's part 1 of our notes. We'll do part 2 when we come back from spring break. We're not just doing a part 2 because you have spring break. It is going to get a little bit harder, so we'll do some harder ones.